All right, so up next we have Christian Amsu, and yeah, apologies in advance. This is going to be a pretty pun-heavy day, but I predict a riot.
Thank you. Hello. So for this talk, there is kind of a promise that it makes. That is that you can use Rust with about 100 different boards and write applications in Rust for those boards while still being portable both between those boards and also not locking into a particular solution. Much of that is, of course, not only the doing of this topic, but the embedded working group as a whole. But yeah, so that's kind of what I hope to make good on in the next 15 minutes or so. Before that, a few words on where I come from. I've been developing IoT solutions mainly in C in bare metal environments, and using lightweight IP as both a network library and kind of part of an operating system. And in the autonomy project, where we're developing or exploring the space of making the power grid accessible to devices to make more efficient use of energy when it is available, we've chosen to go for Rust as an embedded application language because it allows us to share easily code between embedded applications and the backend systems, because people there won't touch C with a 10-foot pole. And also because it gives us what I think is described well as fearless development. So when I build a system and in 5 years or so someone needs to fix something, even with good testing in place, the guarantees that Rust gives me in terms of types and memory help me be sure that whatever they do then won't break the whole system because some detail of the whole setup was overlooked. So on the topic of how we get how we get support for many boards in Rust easily, there's the RIOT operating system, which we can build applications on. So the RIOT operating system is a community project started around 2010. It has a very active community. They're meeting once a year in a summit and meet virtually on a regular basis to keep the flow of code and implementations going. And it is written in C. But it's well usable with Rust because bindings can be generated, and that's the project that we've been implementing in the autonomy project. To have those bindings. So let's have a look at what RIOT does first and then how it can be used. So the RIOT operating system implements, first of all, implements a model of threading, which is similar to threads that you can have on your regular system, just without all those memory separation and process separation measures. It just ensures that you get a stack for different parts of your program to run simultaneously or in good sequence. So that's the whole threading threading subsystem. It implements quite a bit of inter-process communication that interacts with those threads. So you can have mutexes, you can have flags on processes, put processes to sleep and wake them up, etc. Then it also implements all the kind of classical devices that you have in embedded systems, be it SPI, I2C, analog digital conversion, and gives abstractions for that. The RIOT operating system has a very good network stack, or actually several ones, but a kind of central piece where those come together in the GNRC network library, and those network capabilities can then be used on a variety of networks. So you can use them on classical Ethernet just as well as on mesh networks, even cellular networks, and works with IPv6, IPv4, and support for several application protocols is built into the operating system as well. And finally, there's a few additional features that the operating system provides. So for example, there is a There is a shell implementation where applications can register their functionalities, but also expose more generic operating system components, like having something like an if config, where you can inspect the network settings at runtime easily from a serial console or a debug console. So to use that all with Rust, basically the entry point is that an application in RIOT has a main function, so that can be wrapped into that can be exposed to the Rust ecosystem and just calls into there. And those the bindings for that are generated with bindgen. So there's a RIOT syscrate, which gives all the low-level functions, and the RIOT wrappers crate that gives safe abstractions about those. So we'll see a bit more about that later on. Much of the threading in IPC is already well wrapped. So you can, for example, start up a thread from one thread or send a message from one thread to another. Peripheral drivers are only mapped basically in the parts where I use them, so that's something that can still grow. And one of the most interesting parts is wrapping the network parts, because there it is sufficient to map the high-level components, so the application protocols or the network stack in general, and then to utilize that on whatever that particular board has in terms of network capabilities. So when running on a board with Ethernet, you just get your address and can run your server. When you're running on a cellular network, 6LoWPAN, what's or not, connectivity is there. I'll come back later a bit and talk a bit more about how those device drivers are mapped, because there's a very good crate in the embedded Rust ecosystem called Embedded HAL. Those at the workshops will probably have used it, but I'll come back to that. We've heard about how build systems can integrate before, and while it's nice to have cargo as kind of a single entry point, in this implementation we're going a bit of a different route, because the RIOT project has a well-established make-based build infrastructure. So how programs are usually compiled and flashed is by invoking make with the name of the board on which this will all be run, and then tell it to build it, flash it, and open as a terminal for that. That executes a few make statements, or basically calls into a recursive make process, and then at some point can call out to cargo to build our actual Rust code. So the Rust code sits in the whole project as a static library, and all the components of the application that we build are built into a static library that will later be linked together with the rest of the code into a final executable, stripped down, flashed, and finally gives us a shell prompt. Well, let's have a look at how that looks from an application developer's point of view. So not from building, but from writing the software. It's a no standard library. The entry point is described by this macro, which doesn't do much. It just wraps the main function into something that is extern C and will respond to the Rust calling convention. And from there on, we can start to use the RIOT infrastructure to get our devices, in that case an I2C device, and then feed that to some library that is completely unrelated to RIOT that consumes this and gives us sensor readings based on that connected device. Now these devices I've mentioned earlier, they are implemented not as bespoke wrappers, but they implement the embedded HAL traits. So whenever you get an SPI device from RIOT, you can just put it into most of the libraries that expect to get something that is an SPI device in the embedded world, that just implements the respective traits of the embedded HAL crate. This is also what gives the good portability. So if you're developing something in here and later decide that you want to move to another embedded operating system, there is some code that you will need to move. So for example, this part where you allocate where you find your device, that differs from operating system to operating system. On Windows that might be con1, and on Linux that might be def, std, whatsoever. But from the point where you got the device that is an impl of some trait, you can use that and pass it on. For other parts of the operating system, there are no widespread traits to implement, but they look quite a bit like things that you would see in the standard library. So for example, initializing a thread in RIOT has a few more properties than, or a few different properties than initializing a thread on a POSIX or a standard operating system. But it behaves the same way. So when you have a thread, you can either initialize it and pass it static references, or you can have a scoped code like in Crossbeam and initialize with that and wait for all the threads to complete before continuing. And there are some components that don't really have a template yet for what they implement. So they are just bespoke wrappers for that particular purpose, be it high-level application protocols, being low-level networking code, or being sensor access. But I think that we may want to, as a community, think about which of those components that may show up on other parts of the ecosystem as well, we can develop crates that are similar to embedded HAL for, especially on the embedded networking part. So as my time is slowly running out, let's get to what can be gained for this. And given that we are in the free software ecosystem, there should be gains for both sides. So I think that RIOT can profit from this and by getting the API checked, because everything that can be wrapped easily into Rust abstractions that work with lifetimes has good chances of being actually sane in terms of race conditions, and at the same, and so this is at one side confirmation of things being implemented correctly, and on the other side shows up some problems where there might be functions that do expose race conditions, and some of that have already been integrated into RIOT. And from a Rust point of view, this gives us several things. First of all, we get a lot of hardware that is supported basically out of the box. We get access to quite a few networking technologies. And we can also learn things that made the RIOT project successful. So, for example, they have a great community. Well, I think we are already there, judging from this room. They also have easily accessible abstractions for say, basic functionalities that might be useful at the beginning of working with a system. So I mentioned before that there is a support for sensor abstractions. You may not want to use the Sol library when you're streaming data from your ADC sample by sample. But when you're just building a demo project, it can be quite useful to expose that there are 5 sensors on this, and one is a temperature sensor and one is a humidity sensor. And you may be willing to accept that some of this is dynamic information, and then gain support for simple demos on a wide variety of devices. So there's a few open issues. I can, considering the time, probably skip through them, but most of them are, in my opinion, solvable, especially the last one. So whoever wants to join me for the Impl Days, please chat me up. And there's 2 points that I want you to take home from this. One is that this thing is available. We are using it for developing prototypes, so it's not something that has had stable releases yet. But you can give it a try, and it will grow more stable over time. And the other thing is, don't be afraid to log into any of those systems, because as long as you're using good abstractions with embedded HAL or with other abstractions that might still be developed here, you can migrate between operating systems without losing all of your application code. So that being said, what did I not cover? Questions? So the question was whether I managed to get the embedded drivers code exposed via embedded HAL. And yes, that is exactly what I did. So that was largely painless. and it's mostly just a matter of stating that this implements that trait and mapping the functions straight through from embedded HAL to the C wrappers. So the question is, yeah, whether those drivers can be used outside the RIOT project. I can't tell. So I haven't looked into many of the into actually any of the implementations yet. It's free software, so you can definitely look into it. I don't know whether that's. I mean, I think they can be used as a guide if you want to implement native embedded HAL drivers for those devices. Pulling code out of that, I'm not sure whether it would be worth it.
Sounds like an excellent discussion to continue over coffee. But before you do that, please, ladies and gentlemen, put your hands together for Christian.